Hello everyone. So today we are going to study about hazards in pipelining. Hazards. What do you mean by hazards? Hazard is nothing but problem. What problems we are going to face while implementing the pipelining techniques. So now here mainly three categories of hazards we are having. One is structural hazard, second one data hazard and third one control hazard. Structural hazard, it deals with resource conflicts. Data hazard, it deals with data dependency or data conflicts. And control hazard, it deals with branch related conflicts. So today we are going to study about all these things. So these dependencies, they introduce stalls in the pipeline. What do you mean by stalls? Stalls is nothing but a cycle in the pipeline without any input. That is known as stall. So now first let us see about structural hazard. Structural hazard or structural dependency. Structural hazard, it is the conflict in the pipeline which occurs due to the resource conflict. So here what do you mean by resources? A resource, it can be a register, memory, ALU, anything, it is a resource. So this hazard is occurred in a situation when more than one instruction it is trying to access the same resource in the same time cycle. So here for example if you are taking in the pipelining technique we have already seen various instructions at the same time cycle, same time pulse, various sub operations of the instructions which are independent, they can be executed. So here suppose that there are four different instructions we are trying to execute. In time cycle time pulse 1, first instruction, so here we are having various parts of the instruction already we have seen. So fetch the instruction, decode the instruction, fetch the operands, execute and store the output in the memory. These are the various segments we are dividing. In this example we are dividing into 4 segments standard. So here in the first time cycle, first instruction, fetch instruction we are doing. So fetch the instruction in the sense from where we are going to fetch, the instruction is stored in the memory. From the memory we have to fetch. That means the resource which is used is the memory. Right. Now second time pulse or second cycle if you are taking, this is already fetched. So we are decoding the first instruction, simultaneously the second instruction we are going to fetch. So both parts simultaneously they are done in second clock pulse. The third clock pulse, first instruction decoding is over. So next part, that is fetching the operands and execution. So execution part is done. Second instruction, fetch instruction is over. So we have to decode the instruction, and third instruction, fetch instruction we are doing. Fetch instruction in the sense whenever we are getting the fetch instruction, that means it is related to the resource, it is using the resource is memory. Till here it is okay. Now coming to the fourth cycle, in the fourth cycle, first instruction already execution is over. So what is the next segment? Next segment is the output of that segment, it is to be stored in the memory. So here also we are using the memory, memory is the resource. Second instruction we are executing, there is no problem. Third instruction, it is decoded, no problem. Fourth instruction, the first part, first segment, that is fetch instruction. Fetch instruction means again it is to be fetched from the memory. So here also the resource is memory. So instruction 1 and 4 both are trying to access the resource memory simultaneously and in the same cycle. So that gives a conflict. So here you can see how to overcome that, how we can avoid that. One way of avoiding that or overcoming that limitation is the same resource, if it is to be accessed, we will wait till that resource is free. So at each and every time, actually here we have to take the fetch instruction of 4th instruction, but already memory is in use. So, we will delay, we will not take this cycle for instruction 4. Next cycle, instruction 2, memory access is there. That means the same resource again it is used. Here also we will not do anything, we will delay. Next instruction, instruction 3, it is using the resource memory. So, there also we will not do. That is, we will delay until where that particular resource is free. So, we will wait until the required resource, here in our example required resource is memory. So, whenever it becomes available, then we are fetching the instruction. So, this is the one solution how we can overcome this structural dependency. One more solution for structural dependency is, now we do not want to delay that, simultaneously we want to execute. Then what we can do is, in this example, we will divide the memory into 2 modules. So, here we are renaming, actually we will call it as renaming. So, here we are dividing the memory into 2 modules. One module we are calling it as code memory and second module we are calling it as data memory. So, in code memory only we are storing the code or the instruction parts. So, wherever we want to fetch the instruction, we will fetch from the code memory, and in data memory we are storing only the data part. So, when we want to store the data after execution part is over, we want to store the data, we want to store the output in the memory, then we will go for the data memory. So, in this case there is no restriction. In the same cycle, if you are using, here we are using data memory and here we are using code memory. So, simultaneously in the same clock pulse, if we are using the memory also, as we have divided that and as we have renamed that modules, so these two acts as different modules and there is no problem. This is one of the solutions for overcoming the conflict of structural dependency. Next one, it is data hazard or data dependency. So, here there are 3 types of data hazards. One is RAW, read after write, another one is WAR, write after read, and third one is WAW, that is write after write. One by one let us see. First let us see about read after write. So, for example, you take 2 instructions. Instruction 1, we are adding the contents of register 1 and register 2 and the output is stored in register 3. Second instruction, we are adding the contents of register 3 and register 4 and we are storing in the register 5. These are the 2 different instructions we are going to execute. So, here in the first time cycle, in the first time pulse, what we are doing? First instruction, fetch the instruction part we are executing. Second time pulse, first instructions decoding part we are doing and second instruction fetch the instruction we are doing. Third time pulse, the first one execution part we are doing. That means this execution whatever we are doing, that we are doing in the third time pulse. Whereas simultaneously second instruction decoding part also we are doing in the third time pulse. So, here what happens? After doing this, we are going to have the result in R3 and that R3 is to be added here. But by the time this is decoded, this execution part is not over. So, what happens? The old value, whatever previous value you are having in R3, that value it is taken here while you are decoding the instruction. So, there is ambiguity in the output what you are getting. You will not get the expected output and you will not get the actual output which is to be got. So, that is the difficulty here. So, here you can observe that first instruction range is R3, that means the output is stored in R3, and domain, that means from where you are getting the input, that is R1 and R2. Second instruction, output you are storing in R5 and input you are having in R3 and R4. But here what we are having? We are having overcome or overlapping, you can say. Here the actual latest value of R3 you are getting here, and before that only you are going to use the old value of R3 while you are decoding the instruction. That is the difficulty in read after write. Now the last one in data dependency, write after read. Write after read, if you are taking two instructions, again you are taking instruction 1, R2 and R3 contains the product you are taking and storing in R1. In instruction 2, the addition of sum of the contents of R4 and R5 you are storing in R2. So that means here already you are using R2 and here you are changing the value of R2. So first you are writing something and then you are reading. So for example, R2 is equal to 10, R3 is equal to 20 if you are taking. So R1 is 10 into 20, that is 200. Here R4 is equal to 30, R5 is equal to 40 if you are taking. Here R2 is equal to 70. Now what should be the value, final value of R2? That overlapping will be there by using this write after read. The same way we are having write after write. So in write after write, if you are taking 2 times it is written on the same register content. In instruction 1, R1 and R2 the input is taken, the product is calculated and the result is stored in R3. In instruction 2, R4 and R5 they are added and the result is stored in R3. Both you are having in R3 only. For example, R1 and R2 10 and 20 if you are taking, the output R3 is equal to 200 you are having. R4 and R5 50-50 if you are taking, R3 is equal to 100 you are having. Here also the same thing, simultaneously by using pipeline system, if you are going to execute I1 and I2, instruction 1 and instruction 2 simultaneously, there will be overlapping and R3 value, only one value you can have finally. So this instruction, though it is executed, immediately it is overlapped by R3 is equal to 100. That is the conflict which we are having in the write after write. Next one, control hazard you are having. So control hazard, it is based on the branch instructions. So branching in the sense, generally any instruction, if it is a program execution, a process execution if you are taking, in the program counter you are having the address of the next instruction which is to be fetched and executed. And in general we are following the sequential manner, one after another. So first instruction which is to be fetched and executed, that will be there in the program counter, and immediately once the instruction is fetched, it is incremented. So incremented in the sense, next instruction you are going to get, next instruction you are going to get. But here the problem is, suppose if you are having any branch, call, jump, anything if you are having, that means it is taking the control to some other instruction. The address of the instruction where this control is to be taken, it will be as the part of the instruction. When you are executing only you are going to get that. That means till you execute that, till you decode that, first of all till you decode that, you do not know that it is a branch instruction. Then you do not know where it is to be taken, and meanwhile one after one, as usual if you are going to the next steps, the next instructions, the part or the sub operations, sub tasks which are performed, that will be wasted, because here it is a branch instruction. So directly we are moving to some other place, we are not executing the same instruction next immediately whatever we are having. So for example, suppose if you are taking in 100 address we are having I1, 101 I2, but I2, that is instruction 2, it is a jump. Jump means the control is taken to some other place. The address where it has to be moved, it is given here, that is 200. 250 means it is BI1. So here generally what we will do at the starting, when we are dividing as parts, when we are dividing as sub operations, one after another we are starting and going the execution. So what is the expected output when we are performing these operations? First I1 is executed, instruction 1 is executed, immediately after instruction 1 instruction 2 is executed, and as instruction 2 is a branch operation, taking the address which is mentioned in the branch operation, it has to take to 250. In between whatever we are having, we have to skip that. These are not required to be executed. So this is the expected output. First instruction 1, then instruction 2, then directly we are moving to BI1. But in our general pipelining system, if we are doing instruction 1, in the first clock pulse, fetch the instruction part is over. In second clock pulse, instruction 1 decoding part is over, instruction 2 fetch the instruction part is over. Third clock pulse, here already decoding is over, so execution is done. Here fetch is over, so decoding is done, and automatically the third instruction, fetch the instruction, is done. But after completing this, then we will come, during this execution part, we will come to know that it is a branch statement. And also we know here what should be the next program counter value, that is 250. But by that time, in the fourth clock pulse, instruction 1, the execution is over and we are writing back the output, we are selecting the memory where we have to write. Instruction 2, we are executing, and by that time instruction 3, we are decoding, and then we will come to know while executing that the control is to be shifted to B1, not I4, and we are again fetching the instruction which is given in the B1. Now here this fetch the instruction, instruction decode, execution, whatever we are performing, it is of no use. Though we have performed, it is to be cancelled, because we are from there directly we are moving here. This whatever we are performing here, it is to be cancelled. So that unnecessarily we are doing this. The work which is of no use we are performing, because we do not know that here there is a branch statement. So that is the control conflict what we are having, which comes under control hazard. So now here what will be the sequence? From instruction 1, next instruction 2, next we have started instruction 3, and then came to know that it is a branch operation and we have gone to BI1. But here expected output, if you are taking first instruction 1, instruction 2, from there directly we have to go to BI1. So this, not only this, some more steps if we are taking, in between whatever the instructions we are having, we have to skip that, we should not do that. But skipping of that instructions, how we can do? If we know that there is a branch statement, but always we do not know, until and unless we fetch the instruction and decode the instruction, we do not know that there is a branch statement. So here if we know that this is a branch statement, this simply we will delay, we will not do anything. And once if it is decoded, then we will come to know this PC value, it is updated to 250, and in 250 we are having BI1. So the next instruction which is to be fetched and executed, that is BI1. It can understand. So in between we have to delay. When we will delay? If at the starting only we know that there is a branch statement, but there is no chance that we can know 100% that there is a branch statement. So what we can do? Just we can assume, predict, that is known as branch prediction. Branch prediction in the sense, you see, when you are preparing for examinations, just you will predict this, you may get this question in the examination, you will not get this question in the examination. You may be having your own logic, but you will predict. Sometimes your prediction is correct, sometimes your prediction is wrong. So we are not using any machine learning algorithms here, just in simple manner if you are talking about. So here branch prediction if you are taking, this is nothing but at the starting only we will predict that there is a branch statement within the instruction which is available, which is to be executed. So here basing on that we will take some decisions which can be the solution for the control conflict. So here branch prediction if you are taking, two types of branch prediction implementations we are having. In two ways we can implement the branch prediction. First one is static branch prediction, second one is dynamic branch prediction. So once again I am telling, branch prediction, it is nothing but at the starting only predicting that in the following instructions we are going to come over get one branch statement where the immediate next statement should not be executed and the control is transferred to some other address which is mentioned in the instruction. Now let us see first about static branch prediction. Static branch prediction in the sense, as I told you, prediction in the sense 100% we do not know, we are predicting, that is all. So when we are doing some prediction, there are two chances, either our prediction is correct or our prediction is wrong. So now here in static branch prediction technique, what we will do is, here the hardware assumes, always it is assuming the same thing, either always it is assuming that the prediction of having a branch, or always it is predicting that the prediction of not having a branch. So for both the things we are having the logic. So every time we are predicting there is a branch and accordingly we are taking a decision. So we assume that there is a branch, so a branch instruction is going to come. For that, how to handle that, every time we will be following that only. Or we predict that always, so here there is no change, once if it is taking a fixed note of we are getting a branch, every time it is consuming that, it assumes that there is a branch instruction within the instruction, and with that prediction how to handle that, accordingly the system will be there, the logic will be there. Suppose if it is predicting there will not be a branch in the instruction, so accordingly how it has to handle, like that way only it should be. So either it will predict every time, so it may be positive or negative, the result may be true or false, whatever it may be, but again next time again it will predict the same thing, that there is a branch, and accordingly it will be handling. So here if you are taking, suppose if you are predicting timing diagram when the branch decision has to be incorrectly predicted as not taken. So here we are starting with the fetch the instruction, decode, execute and write. So here branch is there, here somewhere while decoding we are getting that. So here what we are predicting that branch is not there, and we are going, next instruction we are starting, next instruction we are starting, and there while this is executed we came to know that there is a branch and the control is taken somewhere. So there actually this is to be executed. So what we will do, till here whatever we have executed that will be removed, that will be assumed that nothing is done, we will go back. So that is one way how we are implementing the branch prediction in the static manner. Second one, if you are taking dynamic prediction. Dynamic prediction in the sense, first we will assume either the branch is the instruction is having a branch and we will start the prediction. After implementation it is wrong, suppose it is wrong. Basing on that result, next time when we are taking the decision, we will change our prediction. So always the next time prediction, it will base on the result of the previous prediction. So in either way, various cases are there how we are going to handle that. So here there are two types, single bit prediction, 2-bit prediction, various things we are having. So here if you consider the state diagram of 2-state diagram if you are taking, mainly we are considering two things. One is branch likely to be taken place. Second one, likely not to be taken place. Likely to be taken place means we are expecting that within the instruction there might be a branch. Likely not to be taken place means we are expecting that there will not be a branch in the instruction. So, basing on this, we are preparing a state chart diagram. So, actually this thing how it is working and all you will be learning in the flat or CD. So, this state how it is moving from one state to another state, how many times it will be moving, all these things we will learn there. Here just the diagram if you understand. So, here suppose you are taking likely not to be taken, branch likely not to be taken, but still branch is taken. So, next time what it will take? It will move to likely to be taken. So, suppose if you are taking likely not to be taken, really it did not take, any branch instruction is not there in the instruction, then it is taken to branch not taken. Again next time prediction also it will be likely not taken only. So, suppose if you are taking likely to be taken, but the branch is taken, so then again next time also the prediction will be likely taken. Suppose your prediction is likely to be taken, but the prediction is the actual result is branch not taken, so the next result will be likely not taken. That means here dynamically the decisions are changed. Each and every time the prediction will depend on the previous result. That means previous case what we have predicted and what is the actual result. Basing on that we are changing our prediction, that is dynamic branch prediction. Not bothering about the previous stage or not bothering about the result, any one thing we are deciding and statically each and every time we are predicting the same thing, that is the static prediction. So, here the same way how we are having 2 state, here we are having the 4 state also. In 4 state along with likely to be happen, not likely not to taken place, apart from that we are having 2 more states, strongly to be taken, strongly not taken. So, again here also the same thing, basing on the previous prediction and the actual output, next time what should be the prediction, this diagram will explain how you have to take, how you have to change the prediction. So, static prediction always in spite of whatever may be the output, you are having, you are holding the same prediction throughout, you are having the same prediction. In dynamic prediction, each and every time basing on our prediction and the actual output, you are going to change the next prediction what it should be.